Welcome, Dr. M here. This lecture is about Grignard reaction, discovered by Victor Grignard, who got the Nobel Prize in 1912. It's typically a reaction between an electrophile and a nucleophile. The electrophile is going to be the carbonyl. The nucleophile is going to be the Grignard reagent that I'll talk about shortly. And it's a 1-2 reaction because your nucleophile is attacking this first atom here, and the electrons between the carbon and the oxygen will end up onto the oxygen. So it's between these two atoms here. So it's 1-2 addition, and it's typically between a ketone. A ketone has the carbonyl, the C-double bond O is called the carbonyl, and two carbons bordering the carbonyl. An aldehyde has a carbonyl with at least one hydrogen bonded directly to the carbonyl, and the other side will be a carbon structure with general alkyl group represented as R. Okay, ester will have a carbonyl with an oxygen directly bonded to it, and that oxygen should be bonded to another carbon, and on the other side should be a carbon containing an alkyl group of choice represented as R. And overall, when the reaction is done, you get a new carbon-carbon bond formed. Also to mention, the carbon of the carbonyl is sp2 hybridized. This guy is sp2 hybridized. When the reaction is done, that carbon, whichever of these carbon of the carbonyls, will be sp3 hybridized. But for other carbon-containing compounds like amides and carboxylic acid, it tends to fail. And why does it fail in an amide? Because of the lone pair on the nitrogen, which can be pushed backwards this way, and that will go that way. Now, you know, the reason why this carbon of the carbonyl is attacked for these three guys is because these carbons are partially positive. These carbons are partially positive. That's why the carbonyl plays the role of an electrophile. Electrophiles generally are positively charged, nucleophiles are negatively charged. Now, if you're pushing arrows like this by resonance, you're actually killing the positive character on the carbon. And you know, like charges repel. If the nucleophile is negatively charged and this carbon is negatively charged, the two are going to repel. There's no 1-2 addition, there's no Grignard reaction. Okay, so that's why amides fail to do Grignard reaction. Now for the carboxylic acid, is going to fail not because of entirely because of the resonance that you're doing here, because remember, esters also have an oxygen that can do the resonance, right? And you think and say and argue that this carbon is not going to participate in Grignard reaction because resonance kills the plus character. But that's not the case for esters, because esters are neutral, but carboxylic acids are not neutral. Carboxylic acids are acids, and we'll talk about limitations of Grignard reaction, and I'll tell you that this hydrogen here is gonna kill the Grignard reagent. Anyway, that said, if you're to rank the reactivity of these guys, the aldehyde is more reactive than the ketone, and the ketone is more reactive than the ester, just because the ester has an oxygen that partially kills the positive character on the carbon. Okay, so here you do have resonance, but as I say, the main reason why the carboxylic acid is not going to do Grignard reactions because this hydrogen here is acidic. The Grignard reagent is basic. Acid and a base, you get neutralization. The Grignard reagent will be killed. So this one the carboxylic acid generally don't do Grignard reaction, but we'll talk about that later on. But how do you prepare Grignard reagents? Okay, it's simply a reaction between an alkyl halide and magnesium metal, and it's usually in dry solvent. In dry solvent, dry aprotic solvent. I'll talk about that later on. Like ether, so the magnesium simply inserts itself between the carbon and the iodine, and very simple, just go ahead and draw your magnesium that is inserted in there. You get that as a Grignard reagent, which is just equivalent to MgI. Same thing here, the benzene ring, the magnesium will insert itself between the bromide and the sp2 carbon, so you get that, you get a Grignard reagent, an aryl Grignard reagent. Same thing with the Cl, you get MgCl. That's why the general formula for Grignard reagent is RMgX, where the R is any carbon containing group, the X is any halogen except fluorine. So you would work with iodine, you'll work with bromine as X, you'll work with chlorine as X. Very simple reaction to do. But just remember the solvent. Just remember the solvent has to be dry and aprotic. Okay, so typically everyone uses dry ether. It could be dry diethyl ether or dry THF. Okay, now let's look at work example between a Grignard reagent that you just made. So the general reaction, the R group will be added onto the carbon. Remember I told you in Grignard reactions, the Grignard reagent is taken as a carbanion, which means it's a carbon bearing a negative charge, which is going to attack the carbon of the carbonyl, which is partial positive. That's why it's an addition reaction. You're adding a group to the other molecule, and then the pi bond will open up. You get 2 lone pairs here, now they're going to have 3. You have 2 lone pairs here, now they're going to be 3. And the MgX will just float around in the flask as a spectator ion or as a counter ion, and then the lone pair will be used to grab a hydrogen to get the alcohol by a process that we call quenching. You have sp2 hybridized carbon here, the carbon here is sp3 hybridized. So the first example here is an aldehyde. Use the 2 carbon Grignard source to add the CH3CH2 onto the carbon. Start by pushing your arrow from the bond to the carbon of the carbonyl. It opens up, and it could attack from the front face or the back face, so you're going to get a racemic mixture of enantiomers, one with the dash bond to the O, and the other molecule structure with one with a hatched bond, the other on the wedge bond. That's why I'm using a wavy line here. You get two options, and then after quenching you still get the 2 options of answers, one molecule with a hatched bond or dashed bond to the OH, the other on the wedge. We call those 2 possible products enantiomers, and they are racemic mixtures because they have equal chance of formation. If you forgot about RNS configuration and racemization, you have to check the link below to remind yourself about that. So the second question, this is an aldehyde still, so you again use an arrow drawing from the bond between magnesium and the carbon to attack the carbon. It opens up, you get an alkoxide, which is a O- sitting on a carbon alkyl group substituent. The MgBr is a counter ion right there. Then we quench again with an acid, you get a secondary alcohol. Now A and B, these products alcohols come from aldehydes. For that reason, you get secondary alcohols. In Grignard reactions, aldehydes give secondary alcohols. Why is this a secondary alcohol? It's because you have two alkyl groups, this guy, the ring, and the ethyl group, bonded to a carbon that carries the OH. So you have a carbon here and you have a carbon there, so there are two bonded to that carbon. Same thing, carbon here, two carbons bonded to that carbon bearing the OH. So it's secondary alcohol for both. All right. Next example, you have a ketone this time around. You have an aromatic Grignard source. So again, same process, attack the carbon, or the carbon it opens up, you get an alkoxide. This time you have two groups which are the same, so it's not gonna be hatched or wedge bond. You don't need to show stereochemistry here because this carbon is not asymmetric, right? And then quench with an acid, you get a tertiary alcohol. Why is this tertiary alcohol? Because you have three carbons, 1, 2, 3 carbons bonded to a carbon containing the OH. So ketones react with Grignard reagents to give tertiary alcohols. For the next example, you're starting with a dicarbonyl compound. On one side is an aldehyde, on the other side is a ketone. Notice we have two equivalents of the Grignard. So in red, put one Grignard close to the ketone, one Grignard close to the aldehyde, and then we are doing the same process, attacking the carbonyl, opening it up, attacking the carbonyl, opening it up. You end up with an alkoxide, and remember here, the Grignard can attack from the front face or back face, or front face, back face, or front and back, back and front. You get so many mixtures, like 4 products from this reaction. So that's why I'm using a wavy line here. You could either have a hatched bond or you could have a wedge bond. This denotes reaction happened by the Grignard attacking from the front. This denotes reaction happened by the Grignard attacking from the back. So I'm using a wavy line for simplicity, but if you're asked to draw all possible products, keep that in mind, that here, yes, you're gonna have those options leading to 4 possible products. Now, so you're going to get enantiomer mass and industrial mass. Again, if you forgot about that, there's a link posted below to refresh your mind. Now this, we are showing wavy line here because this carbon here, because this carbon here is asymmetric. The carbon here is symmetric, this carbon here is asymmetric. So we are attacking that carbon to get a secondary alcohol on this side, and this carbon of the ketone to get a tertiary alcohol this side when the reaction is done after quenching. Okay, so you should know that the Grignard reaction can happen more than once. For the second example, the example E, the 5th example, is reacting a Grignard with an ester. So you are attacking that ester right there. By attacking the carbon, it opens up. Remember, this is only one equivalent. The R group is a methyl. So once it opens up, you get a tetrahedral intermediate like that, and it's still an alkoxide. OET is usually a good leaving group. Alkoxide, the OETs or OR group are usually good leaving groups. So we need to push back to form back the carbonyl, and then the OET leaves, you get a ketone. Now, if you have excess of Grignard, or you want to add a different type of Grignard, once this reaction is done, you can go ahead and add the second Grignard equivalent to attack the carbonyl of the ketone, because ketones do react in a Grignard reaction. Then you get a tetrahedral intermediate. This time there's no leaving group, So the only thing you can do now is to quench it with an acid like that, and then you're going to get a tertiary alcohol. Why is this tertiary again? Because you have 3 carbons bonded to a carbon bearing the OH. So esters like this ester here react to give tertiary alcohols. Alright, so you do practice, do a lot of practice, you'll get it. Okay, there are a few limitations for Grignard reaction, and the very common one is the one that involves solvents. Usually we do Grignard reactions in aprotic solvents. That means these are solvents which don't have hydrogens directly bonded to electronegative elements, so they don't kill the Grignard. For protic solvents, they have acidic hydrogens. The hydrogens circled here are acidic because they are directly bonded to at least an electronegative element like oxygen or sulfur nitrogen. So water, alcohols, as carboxylic acids, thiols, and amines tend to kill Grignard reagents, and you don't want these to be anywhere in the flask. Okay, so an example of that is here. This Grignard being reacted with another compound, for example acetone. I would include it here. For example, acetone. You want to do a Grignard reaction between this Grignard and the acetone carbon containing compound, and there's water in there as a solvent. It's not gonna work. Remember, this guy is basic. This is very basic. Is a strong base. I told you Grignard reagents are taken to be carbanions. So this is a strong base. In presence of a species that has a acidic hydrogen, this guy is just going to grab the hydrogen. And that's what happened here. The equation is not balanced. And that's what happened here. Without balancing the equation, of course, the CH3 MgBi turned to methane, CH3H. The H came from the water. Okay, because water is protic, so all these other solvents will do the same thing. They will kill the Grignard by replacing the MgX with a hydrogen, and you get this inorganic byproduct. So you don't want these protic solvents in the flask. Instead, we use that. We prefer to use dry diethyl ether, dry THF, to allow the Grignard to attack the carbonyl. So Grignard reactions are solvent sensitive. Now, the other point is steric effects. If your Grignard is crowded, like this Grignard here, you have methyl, 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 or alkyl group, alkyl group, alkyl group. It's so crowded, and also the carbonyl is crowded. So if you try to envision, if you try and think like, okay, I'm gonna go in here and fetch for the lone pair that I need to attack the carbonyl, it's not gonna work because the carbonyl is not accessible. Therefore, you get no reaction. That's why I have an X. Or if it happens, going to be very, very poor, discouraging yield. So sterics do affect. That's all for Grignard reaction. I hope you guys get it better and better, more and more.